Hello everybody, this is Chad Williams. Today I'm going to walk you through Lab 5 in Psych 300B, and this is going to walk us through R. What we're going to do is we're going to run an ANOVA, but before that we need to check our homogeneity of variance using a Levene's test. Then we're also going to pick out some R squared and Cohen's F effect sizes. So if you don't have this file yet, go to Brightspaces and get it. It is a little bit long, but you'll note that you actually know a lot of it, so we're going to skip a bunch of it. And that's at the top here. So this first 40 lines of code are things that you already have learned. So it's setting your working directory, it is choosing your data, or loading your data, and then loading your packages. So I'm going to do that here, but I'm not going to walk you through it. So I'm going to first set my working directory. And there's my data set that I need right there. If you don't have that, make sure you're going to get it as well. And then we're going to load this data set. And there it is here. And then before I look at the data set, I'm going to load some packages. And we're going to use the car package today to get a Levene's test and the effect size to get a Cohen's F. Okay, now that that's done, we're going to start looking at our data. What we have is 40 rows, so 40 different people, and 3 different columns. So the first one is the preference of social media. So we have Facebook, Instagram, Twitter, and TikTok. So which of these do you prefer? The next column, which is the column you're going to be analyzing today, is hours self. Okay, so how many hours per day do you spend on social media? So we're looking at whether you spend more time dependent on which you prefer. What I'm going to show you in this demo though is time of day self. So we're going to see, well, what time of the day do you spend on social media? And then does that change dependent on which platform you prefer? So I'm going to be walking you through stuff with this time of day self variable, but you need to make sure you're using the hour self. So you're going to have to change that from this demo and this script. Okay, so we're not going to actually do it in this lab, but I do want to remind you that we should be looking at our descriptive statistics and visualizing our data before we're running any sort of statistics on it, or inferential statistics on it. We don't have time to include this in the lab, but make sure, especially with data that you're using, that you're always doing that first. You want to look at your data before you do anything with it. So the next thing we're going to do is we have to, before our Levene's test homogeneity of variance, we need to manage our data a bit, and that's right here. Basically, each of these columns, so social media preference, hours self, and time of day self that I just showed you, has a int or character. Now int just means integral, so it is a whole number, and these are all whole numbers. And then CHR is character, so this is a string of letters that creates a word. But what our functions need is this character to actually be a factor, so it needs to be specifically a factor. So we do need to change that, and we're going to do that with this as factor function. So remember, you can select your whole data set by writing out the variable name, so social media data. So let's write that here. And if we run that, what we get is all of our data like we were just looking at. No big deal. But we can choose one of the columns by using a $sign. So at the end of this, we can add a $sign. And we could go hours self, for example. Or let's go time of day self. And then so if I run time of day self, all we get is the numbers from this column here. So you can see it starts with 7887, and we get 7887 and so forth. So we could select specific columns by first putting the variable name and then putting a $sign column name. So that's what we're doing in this line of code, where we're first saying our variable name and then our social media preference column. If I just run that, you can see all the Facebooks and Instagrams and so forth. And what we're doing is we're saying replace this column with itself. So this is the same column and data here, but as a factor. So replace it with itself as a factor. And I want you to look here. So this character is going to change to factor as soon as we run this. So I'm about to run it, and there you go. Now it's a factor with 4 different levels, being Facebook, Instagram, Twitter, and TikTok. So now it's ready for the different functions we're going to use. So let's actually start testing the homogeneity of variance. Remember that this test is telling us whether there are differences in variance across our groups. If the variances are too different across our groups, we can't use normal ANOVAs. We have to use a different ANOVA or a non-parametric ANOVA. And I'll tell you about that in a moment here. So the first thing is we want to see if there's any statistical difference between our variances. And we do that with the Levene's test. So this function, which is a lowercase l and a capital T, comes from the car package here. Okay, so if you didn't load that car package, this isn't going to work. Let's walk through this part first. So we see this little tilde here, and we see two of these different variables, but these are actual column names. So we see social media preference is this one, and then time of day self is this one. Again, you need to be changing this here to our self for yourself, for this data, but I'm going to do it with different data, so I'm not giving you all the answers in this video. So what this tilde is saying is basically anything on the right is our independent variable, and what's on the left is our dependent variable. So is there any differences in our dependent variable, so time of day self for me or our self for you, dependent on preference of social media? And that is our what we call our model, okay? And so that's just a little bit of terminology, it's not too important. And so that's what we have here. The next thing we want to do is we have a comma, and we want to say, well, what data frame are we looking at? Because we've only told it what column names to look at, but we haven't actually told it what variable to look at yet. So our data is going to point towards our social media data variable name, which is this one right here. And then finally, we have something where it's center equals mean. So we have another comma and then center equals mean. Now it's just, Levene's test can be run in several different ways, sometimes with the mean, median, and so forth. The median is their default, so we just want to make sure it's using the mean. So make sure you have that. So we're going to run this entire Levene's test, and then we're going to put it into a variable called Levene results. So when I run this, we're not going to actually see anything come up yet. So we have no results yet, but they're all in here. We have our results in here, and you can see even like p-value, blah, blah, blah. But instead of looking in that, we're going to just print it out. So if we print it out, it's going to come down into our console and then give us what we're looking for. So we have our degrees of freedom, so 3 and 36. We have our F value, and then we have our P value here. Now, with the Levene's test, we're only looking at the P value at this point. So this P value is 0.55, which means it's not significant. And again, the Levene's test is seeing if the variances across the groups are different. So here it's saying, no, the variances are all the same. And that's good for us if we want to use an ANOVA. So that means we can carry on and use an ANOVA because there is no statistical difference between the variances of our groups. However, what happens, and this does happen in the real world quite a bit, what happens if this is violated? So we've met it, this assumption of homogeneity of variance, but what if it's violated? We can't run a normal ANOVA like I'm going to show you in a moment here, but we have to use a non-parametric test like a Welsh or Brown-Forsyth test. Now, I'm not going to actually walk you through these tests in this lab here. However, on line 84, we do give you the code in case you need to use it. Okay, so that starts here. You can see here's the Welsh test, and then down here is going to be the Brown-Forsyth test all the way down to there. So if you do violate your assumption of homogeneity variance, you can use those. And then you can see that the Welsh test is best when you're violating your assumption of homogeneity of variance, but you also have unequal ends. But the Brown-Forsyth would be if you have equal ends, so a balanced design. So here we do have equal ends. We have 10 people each. So if you do need to go in here, you should be using the Brown-Forsyth. But that's not always your data, right? Okay. So our Levene's test results are here, and we have met the assumption of homogeneity of variance. So the next step is to run an ANOVA. We can do this in different ways. So the interesting thing about coding languages is sometimes people make the same function multiple times, and sometimes it works in different ways. Today, to do an ANOVA, we're going to use the LM function, which is actually a regression function, but it can handle ANOVAs as well. There are other ones, for example, the AOV function that can also give us ANOVA stuff as well. But here we go. So here in this LM function, the first thing we see is the same model we had in the Levene's test here. And you even see the data here is the exact same too. So far, all we had to do is take this and then copy paste it down to here. This center mean was specific to the Levene's test, so we don't need that down here. Okay, so all of this is going to run ANOVA for us, and we're going to put it in this variable called ANOVA test. So if I run that, we're going to get a new variable over here called ANOVA test, and there it is. Now this looks pretty complicated and not very useful, and that's fine because we're going to find a way to actually look at this data easier. But technically all our ANOVA results are in here somewhere, and we can even open it up, but we're not going to look through it. It's a little bit more organized when you open it up, but it doesn't matter because we're going to be able to use a different function to give us what we're looking for and what we're used to seeing. So here, this ANOVA test, we're going to put it in the ANOVA command, or function I should say. And then we're going to reassign it to another variable called ANOVA results. So if I do that, now we get this ANOVA results variable. And what it does is it does look like, well, there's your p-value and so forth, but again, instead we'll print it out. And now suddenly we see something we're actually very used to. So we see our degrees of freedom, so 3 and 36, our sums of squared, our mean squared, our f value, and here is our p-value. So is this significant or not? And there you go. So this is familiar to you because of class 2. So maybe not in R, but in class, when you calculate these things by hand, you're using a very similar structured table. And that's why we like to use this ANOVA and print it out, because it really just organizes it in the way that we're used to. So there we go. There's my ANOVA results. Is there a main effect here? And I do have a significant difference. So I do have a main effect in my data, again with time of day self, but do you in your data? Okay, so the last two things we want to do is get an R² value, and then we're going to do a Cohen's F value. So funny enough, the ANOVA test actually also has information on an R². And so here we use the ANOVA test. So this ANOVA function, we also have a way of using a summary function. It gives us more information, but what we're going to do is we're going to assign this to a new variable called R² results, because it's going to give us a list of information, but we're only interested in one part of that list, which is the R². So if I run that, we get R² results as a new variable here. And if we pop it open, it again looks pretty messy, but oh, there's our R². So what we're going to do is we're going to specifically, just like we did with the columns, we're going to choose that R² column. So if I say R² results, $R² here, it's going to give us our R². And then I might as well just print it out like we've been doing. And there is our R² of 0.23417 and so forth. So there's our R², and the last thing we need is our Cohen's F. So this Cohen's F function is back up here from the effect size package. So if it fails, make sure that this package is working well and you've installed it. Okay, so the Cohen's F, basically, we're going to again use this same ANOVA test. So ANOVA test, ANOVA test, ANOVA test. We keep reusing it, but in this Cohen's F function now. Just as we've always been doing, I'm going to insert it into a new variable. So there's our Cohen's F variable, or Cohen's F results variable, I should say. And then you even see it right there, but instead we're going to print it out, and it's going to be nice and actually better formatted than the other stuff. And there is our Cohen's F of 0.55. So that's everything you need for this lab. As a quick summary, what we did is we started off by setting our working directory, we loaded our data, we loaded our packages. Again, for real data, we want to make sure we're looking at descriptive statistics and looking at our data visually. And then we managed our data really quickly to make sure it was a factor. We ran a Levene's test to check our homogeneity of variance assumption. We ran an ANOVA, got the results of that ANOVA, then we used that ANOVA to get us an R², and then we used another function to get us Cohen's F, and we are good to go.